Today we will be talking about the Zeeman effect. To start this discussion of the Zeeman effect, we need to understand the principles of an atom. An atom is made up of positively charged protons, neutrally charged neutrons, and negatively charged electrons orbiting the nucleus of the atom, which is made up of protons and neutrons. The spinning of an electron around the nucleus creates an effect called a magnetic dipole moment, designated by the Greek letter mu. This is similar to the way an electromagnetic solenoid acts. Due to the spinning of a charge in a loop, a magnetic field is made, or magnetic force, and we can calculate the direction of the magnetic force using the right-hand rule, which is perpendicular to the spinning of an electron. But to simplify this even more, we can compare a magnetic dipole moment to a ferromagnet with a north and a south pole, just as a magnetic dipole moment has. But when a magnetic field is applied, designated by the letter B, the magnetic dipole moment experiences a torque and will align itself with the magnetic field. The Zeeman effect involves the splitting of spectral lines into two or more emission lines by a magnetic field, by the splitting of p orbitals. Now we must also talk about electron orbitals to understand the Zeeman effect. Now we won't go into too much depth, just the basics and the principles of orbitals. The most basic form of orbital is an s orbital, shown right here. An s orbital is an electron spinning circularly around an atom, and this is found in elements such as hydrogen and helium, with not a lot of electrons. However, we are concerned with p orbitals, which we find in elements with more electrons. Now, p orbitals are one step above an s orbital, and above p orbitals are d orbitals and f orbitals, but we won't get into those, just the p orbitals. We find 3 p orbitals per atom along the x, the y, and the z axis, each looking similar to a figure 8. The y and z axes are up, down, and left, right, whereas the z axis is going into the board. Each p orbital in the x, y, and z axes each have its unique magnetic dipole moment in the y, z, and x axes. When placed in a magnetic field, each of the magnetic dipole moments will align itself with the magnetic field, as shown right here more simply. Because of the orientation of the p orbitals and their unique magnetic dipole moments, each magnetic dipole moment will experience a unique torque, and some will have to rotate more than others to align themselves with the magnetic field. So in this example right here, the x will only have to rotate a little bit, the y a little bit more, or the z a little bit more, and the y will have to rotate the most. And this creates a splitting of energy of the p orbitals. If we look on an energy graph, without a magnetic field applied to the atom, each p orbital has the same energy level. But when a magnetic field is applied, the energy levels change, with the p orbital that experienced the greatest torque being the highest energy. So this would be the y, the z, and the x axes. The Zeeman effect can also be defined as the splitting of spectral lines into two or more emission lines, as shown right here. An emission line is continuous until it reaches a magnetic field and is split into three or more emission lines. The greater the magnetic field strength, the more lines the spectral line is split into. Thank you so much for watching. I hope you could enjoy and learn from this video.